Hello everyone and welcome to this tutorial. Today we are going to talk about the extended Kalman filter and its equations. Also we will explain an application of estimating the motion of autonomous cars, so how to derive the model, how to reflect this model into the state space of the extended Kalman filter. So as you know that the normal or the standard Kalman filter is meant to estimate the optimal state of a linear system, and this linear system, so the linear equation can be formulated into a matrix form, which is the F matrix here and the B matrix, that's for the input transition matrix, and then that's the equation for the propagation of the covariance, as we explained in the previous videos. And at the end here we have the H matrix, that's the one that that maps the measurement space vector. So a linear system is basically the idea that the relation between the output and the input of a certain equation can be linearly distributed or can be expressed in a straight line. Like for example, this this example here. So here we have the input is directly equal to the output. So if we have 1, then it will be 1 in the output, and so on. So basically here we can say that the state is constant, so it's not changing here at all. So the straight line will look something like this if we fit a straight line to the samples that we put here. Another way, if we say that, okay, here we have a multiplier or a scale that we multiply to the input, so we can scale the output. So for this example, so if we input here 1, then here would be 2. If here we have 2, then here will be 4, and so on. So this model also we can fit a straight line to it, and this is still considered as a straight line or linear equation. The third point is that here if we have an offset, so the equation will look like this. So what you can find here as a difference, that the start or the intersection with the y-axis here starts from this point, from 1 instead to 0, and that's basically this term, the offset. So any linear equation can be expressed in this form, y equal mx plus c, where m is the slope or the factor here, and it can be derived by the delta y, the change in the y-axis, divided by the change in the x-axis. And here this term is c, that's the offset, which in this example is 1. But what if we have an equation like this? So this equation will be nonlinear, because if we try to draw samples and project it to this equation, so we cannot fit a straight line to these points anymore, and then we will have some kind of a curve here. So then this is now a nonlinear equation or a nonlinear system. So what will be changed in the Kalman filter? So first, the two easiest things are the prediction and measurement models. So they will be changed to be something like this. So instead of having the matrix form and multiply by the state vector and the input vector, we can have just the equation itself, like here, and also in the measurement model, like here. But for the covariances, things will be different. So here we can't just like substitute f with the equation itself, but then we need to find a workaround or an alternative. So how to deal with propagating the covariance in a nonlinear system. So To do this, let's first understand how the concept of the covariance is propagated. So let's say here we have down here we have the input, and the y-axis here, that's the probability of the distribution. And then here we draw an input with the Gaussian distribution, and from this input we draw like a number of samples, like can be the mean and other samples from both directions here from the mean. And then each sample we propagate through the nonlinear function like this. So what happens is that the propagated outputs, if we check their distribution, we will find that it's not Gaussian anymore. And that's the core problem. So an alternative to solve this problem or a workaround is to use a linearized model of our nonlinear model. So we draw the samples. We have an input, we draw the samples as before, but instead of projecting each point to the nonlinear model, the red curve, we project it to a linearized model around the point of interest. So the point of interest in our case here will be the mean of the input, which is this one. And at this point, we make a linear equation. We come up with this straight line equation, and then we propagate the samples through this straight line. So what happens then is that if we check the distribution of the propagated samples, we find that it's now Gaussian again. So the next question is how to obtain this linearized model. So to have this, we can use the first order Taylor expansion. And that's basically the equation for it, but that's also only for the first order. So it's basically here the function, the nonlinear function, the evaluation of the nonlinear function around the point of interest. So point of interest is A. Then we add here the slope, so the partial derivative of f, the linear model, with respect to x, that's the slope, and then we multiply it with the deviation. So x will be any point around the mean, so any point in this Gaussian distribution, or from left side or from right side. So this is x, and the a, that's the mean of the input here, the point of interest. So x minus a, that's the deviation. And according to the deviation and the multiplier, the slope here, we can find any point along this straight line. So that's basically the idea. So this is the, as we said, that's the slope, or we can also call the Jacobian. And the Jacobian for this exact equation, exact example, will be the derivative of the x squared by dx. So that's basically we get down the power here and then subtract it by 1, so it's 2x. That's the slope for this exact example. So the first order Taylor expansion is basically the approximation of the nonlinear function on the left side here with a linear function, which can be expressed as in the right hand side here, and the slope here we call Jacobian, and that's for 1D. But if we want to have a multiple state vector dimension, so like multiple states in the state vector, then we can construct this Jacobian matrix F. And here I assume that we have a state vector of dimension 3. So we have x1, x2, x3. And to build it, so we take the partial derivative of the nonlinear function f with respect to each element in the state vector. So f1, f2, and f3 here is because we have 3 elements in the state vector. So we have 3 equations in the F model. So each equation map or update a certain element in the state vector. So F1 for updating the element x1, F2 for updating the element x2, F3 is for updating the element x3, and so on. And to see how to propagate the error, so first we need to understand that the covariance or the variance or the standard deviation, whatever, they are all expressed relative to the mean zero. And for one dimension, we say that if we want to know the expectation of the state vector x square, because we want to know the variance, because variance is the square of the standard deviation. So we say expectation of the x square multiplied by the square of the multiplier here, or the slope, the Jacobian. So then we come up with the multiplier square or the slope square multiplied by the variance. So that's for 1D. If we have n dimension of state vector, then the x here will be a vector because now it's in dimension, and here we have the quadratic form of the square here, but in the matrix form. So it will be f multiplied by the expectation of the x transpose, and here the f transpose. So that's basically similar to this term, but that's in dimension. And the output of this will be the f transpose. So p here is our covariance, and this term, as you see, is very similar to the one in the Kalman-filter covariance propagation step. So then the Kalman-filter will look like this. So we replace all the f, b, and the h matrices with the Jacobians that we derive here. So that's the Jacobian f of the state transition matrix. This is the b Jacobian for the input transition, and that's the h Jacobian for the measurement model. And the rest will be the same. So if we check here, the b, it will be very similar. So, but instead that we take the partial derivative with respect to the state vector elements, we take it with respect to the input vector elements, the u1, u2, and so on. For the H matrix, it will be the partial differentiation of the measurement model, the H, if it's nonlinear, of course, with respect to the state vector elements. So here I assume that we have dimension 2 for the measurements. So we have two equations, H1 and H2, or two elements in the measurement vector. Here I assume that we have only two elements in the input vector. So this matrix will be 3 by 2, this is 2 by 3, and this 3 by 3. Now let's talk about the model for the autonomous car. So how to model its motion and how to estimate it in the Kalman-filter framework. So let's assume here we have this y and x axis. So that's the world coordinate, or let's say that's the local coordinate of the vehicle. So let's say here the 0, 0, that's when the system starts, and then the vehicle moved. So here we have at this instant the vehicle is in this position and orientation, heading angle. And the x-axis and y-axis here, these are the body coordinates of the vehicle itself. So it's moving with the vehicle. So we can express any thing in this environment either to the local coordinate or to the vehicle coordinate. So in the next, so now these are the states at this position. So here we have the x, the y, and the theta. So the x here is the x relative to the local coordinates, and also the y and the theta as well. So the theta is the the orientation of the angle between the x-axis of the body coordinate with respect to the x-axis of the local coordinate. So this angle is called the heading angle or the O angle, and the positive sign of the heading angle will be the counterclockwise. So if the vehicle is rotating to this direction, then it's going to, or it's in increasing order. If it's in the other direction, the clockwise, then it will be in the decreasing order, so the negative sign. So then we have here the next vehicle position. So in the model that we will drive right now, it's applicable for the very small changes in the heading angles, and that will be applicable if we have a higher update rate of the software or of the system that we are running. So like, for example, that we are running our system in 10 millisecond, every 10 millisecond, or every 20 millisecond, for example, then we can implement such models. So, but if we have a higher change rates, then we might come up with more complex vehicle model that we can describe later if you are interested, and you can mention or you can write in the comments if you are interested in such video. So the next position here will be like this, and that's here the displacement, so the change of the distance from this point to this point. So to derive the equation, so let's say that first we align the two axes of the body coordinates on each other, and then come up with the equation for the update of the orientation. So the new, as you see, that the new orientation here will be the old orientation plus the delta theta, the change in orientation. So it will look like this. So that's very simple one. But now for the x and y updates. So if we keep them aligned together, so the two body coordinates, then here we draw the displacement vector, and then you see that the angle between these two here is the delta theta by 2, so it's half the delta theta. So what we can see here that, or what we can model is that the vehicle, to move from this position to this position, it rotated like half the delta theta and then moved by displacement delta s. So it came here and then it moved or rotated again by the delta theta by 2 to align to this position. So again, so it has this initial orientation, rotated by half the delta theta, then moved delta s, and then rotated again the delta theta by 2, or the half the delta theta. And this can be modeled in this equation here. So that's the initial position, x position, plus the delta s multiplied by cosine theta at the first position plus delta theta by 2, this difference here. So this angle plus this angle will give you this whole angle, and cosine this angle will give you the this distance here. So this term will evaluate to this distance, and then when you add it to the initial position, so you come up with the new x here. The same for the y. So this term will evaluate to this distance, and when we add it to the initial y position here, then we come up with the new y position. So that's simply the ego motion model for very small changes in the heading angle. And the delta S and delta theta, they can be calculated from the velocity and the heading rate. So the velocity, if Vx here, that's the velocity along the x-axis of the body coordinates, or what we can call also the longitudinal velocity. If we multiply it by the sampling time, the time interval between two successive cycles in the software call, then we can come up with the delta S, the change in distance. And here the same for the orientation. The delta theta can be calculated by if we multiply the heading rate by the sampling time. Now let's reflect this on the state space of the Kalman filter. So, and in this example, we will only apply what we discussed on the prediction model. So the state vector that we have will be x, y, and theta. The input vector will be the change in displacement and the change in orientation that we might calculate from odometry sensors like the wheel speed sensors, the IMU, whatever. So we have these as input, and these are the states that we are estimating. So the prediction model will have three equations, sorry. Each equation here mapped to the update of each state. So the first one updates the x state, the second one updates the y state, the third one updates the theta state. And this will be the equation that we just derived in the previous slide. And here you see that the delta theta and the delta S, these are from the u vector, from the input vector. That's why here I wrote that the prediction model is a function in the state vector from the previous cycle and the current input vector. Then we derive the Jacobian for the state transition matrix, the F here. So we take the equation 1, this one, and we take the partial derivative with respect to the first state, x. And here you can see that it will only result in the evaluation of this term, because here we don't have any dependency on the x-axis. So it will be only this term, the derivative of this term, so it will be 1. Then the second element here will be with the partial derivative with respect to y, and in this equation we don't have any dependency to y, so it will be 0. So the third element will be with respect to theta, and theta we have here in this term. So this term will evaluate to 0, and this term will evaluate to this, because we have the derivative of the cosine is minus sign, and we add the term inside the cosine here as it is, and the derivative of the element of interest here, which is theta, the derivative of it will be brought outside. So the derivative of theta with respect to theta, it will be 1, so it will be 1 outside here, so I just didn't write it. The same in the second row, but here we take the second equation for the y update. So if I take the partial derivative of this equation with respect to y, it will with respect to x first, it will be 0 here. With respect to y, it will be 1, because it will be only this term. And the last one with respect to theta, then it will be like this, because the derivative of the sign is cosine without the negative. So it will be like this. And the derivative of theta is 1, bring it outside, so yeah, just can't write it. The last term, the last row here will be very simple. So the first one is 0 because no x dependency. Second is 0, no y dependency. Last is 1 because we have here the theta. Now for the input transition matrix. So we take the first equation and take the partial derivative with respect to delta S. That's the first input. So it will be simply this term here, the multiplier of the delta S. So cosine theta plus delta theta over 2. That's very simple. The second element here in the first row will be the same equation, but the partial derivative with respect to delta theta. So it will be very similar to this one here, but this time instead of taking the derivative of this one, it will be the derivative of this one here. So the derivative of this one is half, 1 over 2. So the equation here will be the derivative of cosine is minus sine, so minus sine here, and then we take the derivative of this element here outside, so it will be half, and the rest here is the same. So the same for the second row, and for the third row also will be here 0 and 1 because no dependency to delta S anymore, and here we have only dependency to delta theta, which is 1. So now we have everything we need to do the prediction step. So the F matrix, the B matrix Jacobian, the Q matrix, here we have another video which explains how to derive it. So you can try to derive it for this model here and write it in the comment below, and I will check it myself. And of course here the F, this is a very simple one, so here just substitute here the equations as they are. And the output from this prediction step will be that we have given the inputs that we measure from the odometry wheel sensors and the inertial measurement units like the gyroscope, accelerometer. We can have these kinds of updates, so the trajectory of the vehicle along the uncertainty at each position. And since here we only talked about the prediction step, so there is no update yet. So every time we execute the prediction step, we have more uncertainty in our estimate. So that's why the ellipse here increases, and the ellipse increase in the y direction here, given that we assume that the heading angle has more uncertainty than the longitudinal change in position. And this results is in that when the vehicle is driving straight forward, then we are unsure if it's really straightforward or maybe there is a kind of drift to this position here, or even on the other side. Depends on the sign of the offset of the gyrosensor, for example, or the wheel model that we have. If the vehicle started to take a turn here, then we will have a correlation. So the ellipse will start to have some tilt angle, as you see. So now the last thing in this video, let's talk a bit about the different kinematic models that can be used for the vehicle state estimate or the position estimate. So on the right side here I made a schematic for the vehicle. So here we have the four wheels, here with the steering. The vehicle, as you know, that when the wheels started to steer, so the left wheel might have a different angle than the right wheel. This we can call in this situation the inner wheel, because that's on the inner side to the rotation, point of rotation, and that's the outer wheel. So the inner wheel will have more angle than the outer wheel, in order that the tangent, the orthogonal line, the perpendicular line that we draw from each wheel should intersect at the point of rotation. here. So if we draw a perpendicular line from all the wheels, they must intersect during vehicle having a turn. So the wheel in the middle here, that's we call the virtual wheel, because that's could be the average of the angles of these two wheels, the right and the left. And here we can use it for a kinematic model, which we call the bicycle model. And the wheel angle can be described only in one value, which is the angle of this virtual wheel, which is the average of these two wheels. And here we have we might have the velocity of each wheel separately that we can measure from wheel encoder or wheel sensor. And here we have the body coordinates of the vehicle, so we can express these two velocities in the velocity of each wheel in one velocity for the whole vehicle, that's the Vx, and Vy, that's the lateral velocity in case the vehicle is moving very slow or there is no drift from the vehicle or side slip, then this velocity will be 0. If there is a side slip or drift, then it will have some value here. That's the heading rate of the vehicle, the change rate of the heading angle. And here we have two main configuration parameters. So one is the track width. So that's the distance between the rear wheels, the center of the rear wheels, that's we call track width. And here we have the wheelbase, that's the distance between the center of the front wheels. So let's derive the first model. So to come up with the vehicle velocity, we can take the average of the right and left wheel. So that's basically it. So the average is the summation over 2. So here, as you see, that if the vehicle taking a turn, the velocity, the inner velocity of the inner wheel will be smaller than the outer wheel, and the average of them is the total velocity at the center of the rear axle here of the vehicle itself. Vy, we assume that it's 0 because we assume that there is no side slip. And for the heading rate, we can drive it in two approaches or two models. So the first one is the differential model. We take the difference between the right and left wheel velocities and we divide by the track width. So that's simply it. Or we can have use the bicycle model. So if we have a sensor that measures for us the steering wheel angle, and then we can convert it to get a prediction for the sigma f value, so the actual wheel angle on the road. So then we can use such a model, and it will simply be the velocity of the vehicle that we calculated from the first step here, multiplied by the tan of the wheel angle divided by the wheelbase. So that's it. So now we have the model to calculate the longitudinal velocity, the velocity on the x-axis of the vehicle, and the heading rate, either with the differential model or with the bicycle model. So the heading rate can also be measured directly from the inertial measurement unit sensor, specifically the gyroscope. But with the gyroscope, it needs more processing, like to estimate the sensor offset and do some calibrations before really trusting it. And this calibration can be done during standstill in order to know exactly the offset of the sensor. And that's it. So the last thing that I need to mention is that so we can have these states, the velocity on the x-axis here, the heading rate in a separate Kalman filter, which is processed before the motion Kalman filter that we just derived in the previous slide. And I would like to you to write in the comment also as a homework how do you see the model of the other Kalman filter will be to estimate these two states, how the state vector will look like, what's the inputs, what's the measurement. So you can use the IMU, the wheel speed sensors as an input, the steering wheel angle, whatever, and just put in the comments how do you see the system model will look like, and how do you think the Kalman. Don't forget to like and subscribe to the channel, and see you next time.